Let me just welcome Professor Mukul Sharma. He's a professor in our Hildebrand Department of Petroleum and Geosystems Engineering, where he has been for some 35 years. And he has served as chairman of the department. His current research interests include hydraulic fracturing, oil field water management, formation damage, and improved oil recovery. And we are proud that Dr. Sharma is a member of the U.S. National Academy of Engineering. His degrees are in both chemical and petroleum engineering. And with that, I'm going to pass it over to Mukul to talk about the Water-Energy Nexus.
Thank you, Hillary. I'm going to put up my slides and please tell me if you can see them.
Yes, I can see them. Perfect.
Okay. So I'm going to go through, and how much time do I have, Hillary?
Let's see. You have until 3:20.
3:20. Okay. All right. And that includes the questions, or?
No, that's when we start the questions at 3:20.
Oh, okay. Yeah. Great. Thank you. So, well, thank you for inviting me to this workshop, and I wanted to talk to you about a really important topic, which is how energy and water are related to each other, and how we can see this issue. There's been several talks, several people who've talked about the water-energy connection, and there's many ways to think about it. So one way to think about it is shown in this chart, where water usage in the United States, energy being the single largest use of energy, including things like irrigation and public supply and so forth. But you notice that the biggest block here is thermoelectric power, and I think it's certainly true that in terms of fresh water usage on the surface, power plants do use a lot of water, but they don't really use it in the sense that it's used for cooling or other purposes in the power plant, and then it's circulated back. So if you go down to the Fayette power plant down here on 71, you'll see, it's sitting next to a lake, and most of these power plants are sitting next to a lake. And so the water is essentially circulated through the plant and fed back as a warm stream back into the source from which it was taken. But this is not the only way to look at water and energy connections, right? In fact, you can think of water as being used for energy production in a couple of different ways. So you can think of cooling technologies and so forth, alternative fluids for drilling and fracking and so forth, and process efficiency and materials and so forth. So there's connections that go far beyond just using it for cooling power plants. You can think of energy not only being used for energy production, but what happens to the water that's produced during energy production. So for example, what happens if you have a tremendous amount of wastewater being produced, or produced water coming in from these unconventional sources. So for example, oil and gas produced waters, water from carbon sequestration, brackish groundwaters, and so on. All of these oil and gas produced waters make up a very large volume of fluid that has to be disposed of in some way. And in fact, it is one of the largest man-made waste streams that we have out there in terms of being able to deal with this very large volume of water. So what I've done is I made an estimate of what the volume of this water actually might be. There are no official numbers for this, but we estimate that there is over 300 million barrels. And if you want to convert that, that's 48 billion liters, or about 1.7 billion gallons of water that is being produced every day, right? So around the world. And the question that we get asked all the time is, well, there's a tremendous amount of water that you are producing, and that is a very large volume of water. As I said, one of the largest man-made, quote unquote, waste streams, right? Most of this water is extremely brackish, as it has a lot of salt in it, so you can't really use it on the surface for irrigation and things like that. And the question then is, what can we do with this water? Well, the answer to that is that about 91% of this water is returned back into the subsurface through injection wells. So most of the water is re-injected. Some of it is recycled and reused, only about 2%. And what can we do in terms of providing technology to deal with this very large produced water stream? So I'll talk a little bit about what kind of things that we have been working on in this area. So I'll talk about this in three important areas of research. One is, of course, produced water and frac water reuse and recycling through the reuse of this water in fracturing, in hydraulic fracturing. There are fairly large volumes of water that are used in hydraulic fracturing. So it may be 100,000 barrels of water being used in a single well or more. There's another interesting development that has happened in the last year or two, where people are talking about extracting valuable minerals from the water. And I'll show you a little bit about what we've started to do on looking at extracting lithium, for example, from this water. The second area of research I'm going to talk about is how can we reduce the amount of water that is used in oil and gas production? So how can we actually not use fresh water in large quantities in these in the production of oil and gas? And then the third area I'll talk about is produced water disposal or re-injection, and what can we do in this area of produced water disposal, and what are the important, interesting questions, and what has been done in this area. So let me start by talking about area one, which is produced water and frac water reuse and recycling. How much of this water can be recycled? What is the cost of reusing this produced frac water or produced oil field water? And what is the most effective technology? Are there any cost savings associated with this? And what are the most important improvements in technology that we can achieve? So if you look at some of the produced water, in this case, I'm showing you produced frac water, you see that there is a proportion or a certain fraction of this that consists of really small, 0.44%. So there's some proppant in here, there's water in here, but this small percentage contains some chemicals. So it may contain bactericides, gel breakers, it may contain a little bit of acid, friction reducer, and so on. Most of these chemicals are things that can be removed, and if they can't be removed, then you can certainly re-inject these chemicals without any serious consequences. But in many cases, if you want to reuse this water for fracking, then many of these chemicals need to be at least reduced in quantity. So removal of polymers, scale control, including norms, naturally occurring radioactive materials, oil and grease control, soluble organics, like decreasing the total organic content, the control of suspended solids would be important, microbial control, and then perhaps even desalination, which is by far the most expensive thing that is done with these waters. So people have tried various different things, and I'm not going to go through the details of the strategies for water pre-treatment and reuse, but there's brine coming in, produced water and flowback water from fracs coming in, and then you can do a pre-treatment to remove solids and suspended materials. You can use membranes to remove things. You can do vapor compression or evaporation, and then get highly concentrated brine, which can be disposed of in class 2 disposal wells. So this may be one strategy for doing this. All of this, of course, is expensive and costs money, and convincing people to go through and doing this may not be a trivial process. There's been a lot of interest in using membranes for treating produced water. And we have had an ongoing program in this area for the last, I guess, 20 years. But the problem, of course, is that oil field water, most of these membranes have been used for seawater desalination and purification. And seawater is relatively clean compared to produced water. So what you end up with is a tremendous amount of fouling with internal and external these particles, as well as dissolved organics contaminating the membranes and causing problems with the life of these membranes. So we've approached this problem by modifying these membranes in different ways, by putting in hydrophilic grafts on the membrane surface, by putting in using composites that are more hydrophilic. And the approach that seems to work the best is to actually put in this hydrophilic coating and using existing membranes. So we use existing RO, ultrafiltration, microfiltration membranes, and then treating them with very inexpensive chemicals that will allow us to then go from something like this, which is a membrane that's been fouled or contaminated with produced water, to looking something like this, where the membrane is actually much less contaminated because the oil and the organics don't stick to it as much. So we've done some field trials of this in the Barnett Shale, for example, where you basically have non-coated membranes being compared with coated membranes and seeing how their performance is relative to one another. And of course, what we have found in many of these studies is that the coated membranes do a lot better than the uncoated membranes. They last a lot longer, and we can certainly use them for extended periods of time compared to these uncoated membranes. There's also desalination methods that people have used for mechanical vapor recompression. And this is a picture of one of the Devon sites, which processes about 6,000 barrels per day to remove the salt so that the water can be recovered. Again, a very expensive operation, not something that you could do on a routine basis because of the cost. There's filtration things that you can do to remove the suspended solids in various forms. And these are pictures taken from the field of various applications of trying to recover the water so that it can be reused either for hydraulic fracturing or for surface use. At the end of the day, what we have, the cost of water treatment in most applications makes it uneconomic in most situations, right? The filtration, the desalination, the removal of polymers, the removal of dissolved organic materials, and so on, makes the cost of the water treatment prohibitive. And when I say high, what I'm talking about is the typical cost of produced water reinjection is of the order of a few cents per barrel, whereas the cost of treatment could be as much as 10 times or even more. So it becomes very difficult for an operator to justify doing a lot of treatment in these for these produced water if they are dirty. Now, there are places where the water is relatively clean. It has relatively few suspended oil droplets, relatively little organic material dissolved in it. And so in those cases, people are using produced water, particularly in gas wells, where the water that comes with the gas is relatively clean, and you can use this as a fracturing fluid. And in many cases, most of it is used in an untreated way. So produced water reuse for fracturing is something that has been tried and is being done in a very limited way because of the cost of treating the water and removing all these materials from it. A more recent thing that people have been talking about, which has not been done before, is the extraction of precious metals from the water. Lithium, as you all know, is the primary building block for a lot of the lithium-ion batteries that are being used in things like electric cars and many other things. And so there's a huge demand explosion for lithium. And lithium has traditionally been mined. There is only one lithium mine in the US that currently exists. So there's been an idea floated, which has been around for a long time, but for the first time being considered very seriously, is to take some of these oil field brines and extract lithium from it. And so it's an active area of research right now as to how you might be able to extract lithium from some of these brines. Just to give you an idea, seawater contains just a few parts per million of lithium, whereas some of these reservoir brines, and just a few of them, not all of them, but a few of them contain up to 250 ppm of lithium. The problem is that you also have about 50,000 parts per million of sodium and other salts in it. So the challenge has been to try to extract the lithium, but leave the sodium and the other ions in the solution. So we are actually beginning to do some work on looking at how to extract lithium from these brines. It's an active area of research, not just here, but in many places, because environmentally, this is probably the least environmentally damaging way of recovering lithium. Because if you do mining, you have to have these massive open ponds, which you evaporate the water and the salt settles down and you can extract lithium from the salt. So, and like I said, there's only one of those mines in the US. Most of the lithium comes from South America or from China. And that's been our source of lithium. So extracting valuable minerals from the water is just starting to happen in the US. And I think it's going to be something that you have to watch out for, because we do need the lithium to provide for these lithium-ion batteries. Area 2 is in reducing water use in oil and gas production. And I'll talk about a couple of these topics. The amount of water usage for oil and gas production is shown here. This is the data that is available to us today. You can multiply these numbers by about 2 to get the more current numbers. And so you can see about 10,000 to 36,000 cubic meters per well. If you want to convert that to barrels, you have to multiply by 6. And if you want to convert this from back then to now, you have to multiply by a factor of 2 again. So you're talking about something in the neighborhood of 100,000 to 200,000 barrels per well for each. And of course, there's thousands of wells being fractured. So you can see that there is a very high intensity of water usage in all the shale plays that are being developed, whether it's the Bakken or the Marcellus or the Eagle Ford or the Wolfcamp. There's a tremendous amount of water being used in oil and gas production. One can use produced water as a source for this fracturing water. The problem is that the fracturing water that we used some years ago had to be fresh water. In other words, you had to use fairly low salinity brines, because the polymers that were being used at the time were not very tolerant to high salt concentrations. And if you look at the salinity of the produced brines, you can see that some of these brines are extremely brackish. Just to give you an idea, seawater is about 35,000 parts per million, which is about 3.5%. So seawater would fall into this category. All of these are, this is 50,000 parts per million, this is 100,000 parts per million, this is 200,000, and over 200,000 parts per million. So this could be as much as 10 times the salt concentration of seawater. So some of these areas are extremely high in salt concentration. Some of them are not. I mean, some of them are fairly fresh. So you look at these ones, it's less than 10,000 parts per million. So if you were in this area, reusing this produced water for hydraulic fracturing would be feasible because the salt concentrations are relatively low. If you're in these areas down here or even down here along the Gulf Coast, you might have a much harder time. And in fact, in West Texas or in New Mexico, you might have a hard time being able to use, because the salinities are usually above 50,000 parts per million. So slick water fracs are the most common way of fracturing these wells. And traditional slick water uses polyacrylamide polymers, and they have required the use of fresh water in the past. However, in the last 5 or 6 or 8 years, there has been new friction reducers that have been developed, new kinds of polyacrylamides and other polymers that can tolerate up to 100,000 parts per million of salt. And so now you can use the produced water, if it's relatively clean and free of oil and things like that. You can use the produced water to actually prepare the fracturing fluid, because you can tolerate salinities up to 100,000 parts per million, and for some polymers, even higher. So this transformation of being able to use brackish water as opposed to fresh water in the frac fluid means that you can actually recycle and reuse the produced water for fracturing. And this is obviously a double benefit. It reduces the need for fresh water, and you can actually in some areas dramatically reduce the need for fresh water. And in some places that is absolutely crucial, because you may not have a good freshwater aquifer available to source the water from. And the second thing, of course, is it reduces the volume of produced water that has to be disposed of, right? So if you can reduce the volume of fluid that has to be re-injected, that's a big plus as well. So this is a win-win for the operator if you can do this. And so without desalinating, it saves you a tremendous amount of cost. You can filter the water, and filtration is relatively inexpensive, and remove any suspended materials in the water, and then you reuse that water for hydraulic fracturing. And this is being done quite a lot. For example, in the Marcellus, where the salinities are reasonably high, they actually mix fresh water and produced water to get the salinity to around 100,000 parts per million, and they use that as the frac fluid. And in other places as well, people are beginning to use this. So the development of these new friction reducers or new polymers has really helped in being able to reuse this produced water. It is possible to create hydraulic fractures using other fluids besides water. So you could use CO2, you could use CO2 foams, you could use nitrogen, you could use nitrogen foams, you could use liquefied petroleum gas, and so on. And each of these has its pluses and minuses, which we don't have time to really get into in any detail. But in terms of wellbore hydraulics, or the pressure required, and the fluid recovery and the cost and so on, I put question marks in some of the areas of cost, because it really does depend on where you are in terms of what the CO2 is going to cost, or what the nitrogen is going to cost. It's very different in South Texas, for example, compared to West Texas and so on. So it really does depend on this. But it is possible to replace water with these fluids. A relatively small proportion of the wells are fractured with these fluids in the US. So the last data that we have available, only less than 5% of the wells use these fluids for hydraulic fracturing in the US. The percentage is about 25% in Canada. So it's much higher in Canada. Not sure exactly why, but I think it has to do with the size of the frac jobs, and also the availability of some of these gases in Canada. And so we have actually done a lot of work on looking at the benefits and trying to convince people that actually well productivity can be improved significantly by using some of these gaseous fluids, particularly in depleted and water sensitive formations. You can get much better performance if you use gas. This is the productivity of the well. If you use gas in all the stages, you get better performance. The difficulty is the availability of the gas and the cost of the gas relative to just water. So that's been the big, and you can reduce the water usage drastically if you would do that. The last topic I'll talk about, since my time is, I only have about 3 or 4 minutes left, is area 3, which is produced water disposal or reinjection. This is something that my research team has worked on for the last 35 years, and we've done a lot of work on produced water and frac water reinjection, looking at modeling injectors and how these injectors behave over long periods of injection. This is not just for reinjection, but it's also for water flooding of these oil reservoirs, etc., which is the bulk of what most of our oil production from mature reservoirs in the onshore US comes from. And then understanding how these fractures, these injectors influence oil recovery. Looking at fracture growth in injectors. Are the fractures going to be contained within the zone of interest, or are they not? What are the factors that control the growth of these fractures? And then injection into soft sands. A lot of the offshore Gulf of Mexico injection is happening into very soft sediments, almost like beach sand. And then what happens if you have oily water injection? What should be the water quality in these? And we've looked at probably about 50 different case studies around the world for water injection and the consequences of water injection on the fate of the water. Where does it end up? Where does it go? How do these fractures grow? How are they contained? What can you do in terms of understanding how to inject, what pressures to inject, what rates to inject, and what is the injectivity of the well going to look like over a period of 10, 15, 20 years of injection, right? So a lot of this work has been done here at the university. There are many dozens of publications, which obviously we don't have time to get into, but there's a big body of work that's been done in this general area, right? I just put in one slide that shows where this water is typically injected. It's typically injected into fairly deep formations, far away from freshwater aquifers and so forth. But there's always the concern of, where is the groundwater, where is the potable water aquifer sources, and where are you producing from, and where are you injecting into? And that's been, of course, a big area of concern that people have had. So I think my time is just about done. So I'm going to stop right here and I'll take questions. I can stop sharing and I'll take any questions that you might have.
Thank you, Mukul. I'm going to pass it over to Margaret for fielding the questions. And while she's getting set up, I have a question I want to ask you, Mukul.
Sure.
So can you remind me, I remember I was sort of startled by the difference, but you mentioned the concentration of lithium in seawater compared to the concentration in these formation fluids.
Mm-hmm.
What was that difference again?
So it's under less than 10 ppm, less than 5 ppm in most seawater, and it's about 250 ppm in some of these brines. Not all of them, but in some of them.
Okay.
So about a factor of 20 to 50 more.
Okay. So my question was on when you showed the graph of the salinity of these different brines, seawater's like 3.5%. And then there was the highest category. I'm just going to put 35 in the middle of that. So that's just like a factor of 10. So I was curious, how is it that this lithium gets so much more concentrated in these formation waters than just the salts?
Yeah.
What are the processes?
Yeah, so that's an interesting geological question, and you being a geologist, I should be asking you that question.
That's why I'm asking you, because I don't know the answer.
So it all depends actually on the origin of where the water came from, and so
yeah.
In many cases, if the source of the water and then the clay content of the formation, both of them control the lithium content. And there's actually several papers that have been written on the origin of lithium. So for example, in the Smackover in South Texas and along the Gulf, the concentration of lithium is high, but if you go above or below, the concentration of lithium is not that high. And so there are questions about exactly, there are geologic models that people have built as to why this is happening, but it's a complicated question.
Okay, yeah, so maybe those clays you talked about might be a big factor.
Right.
Okay, thank you. I'll pass it back to Margaret now.
Mukul, it was a great talk, very interesting. We have one comment from the group. I'm not sure if it was just a comment or a question, but I'm going to go ahead and read it.
Sure.
And then for everybody else, remember, if you have a question, you can put it in chat or you can use the raise hand function. But it says, it seems that private and government entities would invest more in desalination. If we ever break that technology, it would be huge. I mean, based on your research and things, do you see progress?
Yes, so desalination has been sort of the holy grail for quite a while. Like I said in the talk, there are many ways of desalinating brines. Most of them are targeted towards desalination of seawater. There are no technologies that we currently have in the membrane field that would desalinate something that's 100,000, 150,000 parts per million. So membranes typically work till about 50,000 parts per million. When you get to much higher salinities, the only way to desalinate is, that we know of today, is to actually boil the water off, which is a very energy intensive process. So to get the water to boil off and leave the salt behind, leave a concentrated brine behind, requires an incredible amount of energy. And so that has its own consequences in terms of CO2 generation and so forth, right? So desalination is a very attractive thing, but it is expensive. And that's why it's not very widely used. In fact, very seldom used in the oil field. Whether you do it by evaporation or whether you do it by membranes, both of those processes have their limitations. So it would be great if we could find a new way of doing it, but so far we are limited in what we can do. Lots of research going on, though. Lots of research going on.
We have a comment, and my chat function is kind of marginally functional here.
I can read it if you like. I can see it.
Okay, about the West Virginia work?
Yes.
Okay.
So, Himanshu Vyas is asking, I got disconnected midway, so not sure if this was covered. West Virginia has a location where there is active work being done to try and recover rare earths from brines. Federal government is also involved via DARPA, so it is high priority. That's right, Himanshu. There's actually several projects going on right now, both among funded by the government, but also funded by private equity. The one that is the most high profile these days is the one in California, actually, where in Imperial Valley, where they have these hot springs, they're actually trying to extract lithium from those. And so there's some very interesting work going on in different places in the country. That particular thing is being funded by the Gates Foundation, I think, or one of the private equity groups in California. But there's opportunities here in Texas as well. So I think there's, and that's the ones that we're going after. We're doing since starting this summer, we've done some preliminary work on identifying appropriate sites for actually doing this. There's actually very little data on lithium concentrations in brines in Texas. So we need to get a hold of a good database or gather some data on that in the coming years.
So a similar, at least in format, type of question that I asked Kishore was, there's all those different types of enhanced oil recovery techniques, a lot of different things for managing produced water. Where does an oil and gas operator start? And, do you have any implications for people that are regulating it?
That's right. So the one of the big things that has happened in the last decade is that, as I showed you earlier, a vast majority of the water that we produce is re-injected, and it's been re-injected for over 100 years, right? East Texas and so on are places where we re-injected water for literally over 100 years. Most of these places do not show signs of seismicity, for example, whereas in places like Oklahoma, where there has been signs of seismicity, water injection is severely curtailed, right? And in some places, for example, in the Dallas-Fort Worth area, there's been some issues reported with large volumes of water being injected. So I think one of the concerns that people have, and this is an active area of research as well, in some groups at UT, not mine, but some other groups here at UT who do seismic type work, is what do you do with the water to try to minimize the amount of water that you're injecting, so you don't inject these very large volumes of water. In West Texas, for example, the volume of produced water is increasing. Every year it goes up. And a lot of that is re-injected, and there's concern that at some point there will have to be an alternative found. So I think that's going to drive people towards trying to minimize the amount of water that they're re-injecting into these disposal zones and using the water, for example, for fracturing or something like that. So everybody is trying to find a solution to, and the use of these salt-tolerant polymers is a great way to address that need. Is use the water, store it, and then use it for fracking. That's one great way of doing it. Desalination or filtering and so on is very expensive, but if we have to do it, it'll be done. I mean, it's something that if it needs to be done, will be done at a high cost. At a high cost.
There are companies that are popping up now, business opportunities, I guess. There's just simply midstream water companies. They're taking produced water, frac water, they have freshwater sources. Are they part of this research and work that you're doing?
Yes, there's a lot of midstream companies that essentially gather the water. Most of the research that we do is funded by the large E&P companies or by DOE. So there's relatively few companies that are in the midstream, and partly because they are relatively small companies. They aren't very large in terms of being able to support and fund big research projects. But they do utilize the technology that comes out of here. So I know another faculty member, for example, that had a startup that actually went out and applied some of these modified membranes into the field. Yes, there are mid-sized companies that are interested and do work related to more research type work and technology implementation. But it's a tough business to be in, especially in this downturn in oil prices and the energy business. A lot of them have gone out of business, primarily because the need for treating water has dropped. People are not willing to spend the money to actually treat the water. And from a business cycle point of view, it's been a rough time for many of these companies.